SP Harsa from Mechanical and Industrial Department, IIT Roorkee. Today in this lecture we are going to discuss about the forced vibration, that you see when the forcing frequencies are there on any system, then how the system is biperiodically excited. So, as we discussed in the previous lecture about the damping, we know that damping is playing a crucial role in controlling the entire exciting frequencies or the vibrations. So, today you see like when the system is biperiodically excited, then how the damping is again you see like playing a critical role we are going to discuss. Second feature which we are going to discuss about, that you see when we are talking about a 2 degree of freedom system, then how we can frame the equation of motions for that. Because we know that when we are talking about the 2 degrees of freedom system, then there is a Newtonian mechanics in which you see we just want to set up the force configurations, and based on that we can simply generate the 2 equations which are simply reflecting both degrees like of the freedom. We know that there are 2 like the different coordinate systems are for 2 degrees of freedom. Then you see how we can make the coupled equations, and then how we can generate you see here the solution from these 2 equations. What are the corresponding we can say natural frequencies or the characteristic roots, and then what are the corresponding you see the relative displacement of the masses or something you see here, which we are generally saying that the eigenvectors or the vibration mode shapes. So, like in the previous lecture we know that like as far as the damping is concerned, there were 3 modes, and all the modes are like playing critical role in formation of the complete damping. So, that is why you see we know that it is really like hard to say that this is the overall damping phenomena, because the damping is coming right from the intermolecular motion to the surface rubbing action to the fluid, whatever the fluid is available at the like the surfaces. And then what exactly the like the total resultant of the damping is, it is really hard to calculate. So, sometimes we are giving like some numerical value, it is you see irrelevant to say that this is the overall like representation of the damping is, because you see the damping is coming out from the, as I told you, the intermolecular motion and all other aspects. So, again you see here whenever we are talking about the damping, we need to be very careful that what kind of material which we are using, what kind of like the lube oil which we are using there, and what exactly like the rubbing actions are there when the dynamic motion is happening. In today's lecture you see we are going to discuss about the free and forced vibrations on the 2 degrees of freedom, like on that. So, as we discussed about the single degree of freedom system, that can be easily like changed into 2 degree by simply coupling the similar kind of the structure to the another form. So, in that way we can produce the same mechanical system which can describe the 2 coupled differential equations, since it is like a discrete system. So, we have ordinary differential equations there itself, and then you see we can form 2 equations which can represent the 2 degrees of freedom system. To specify the state of the systems at any instant, we need certainly you see the dynamic parameters with respect to the coordinates x1 and x2, in which these 2 whatever we can say the masses or anything are simply oriented like in their configurations. And then you see here based on these 2 degree of freedom system, we can find out that where we can apply the absorber through which we can effectively control either x1 or x2 of the amplitude of the vibration. So, that is why like this in 2 degree of freedom system, it's a further we can say the refined system in which we can effectively control the vibrations at the root cause of vibration. We can apply this concept to any of the equations or the real application, like we have say forging hammer and the anvil on the ground isolators. We know that you see when we are using that, there is you see the contact region in between, we can say the hammer and the anvil to the surface. So, wherever you see the contact surface is there, we know that this is somewhat a representation of the elastic deformation, or we can say we can represent this elastic deformation by the spring. So, as you can see on your screen that what we have the hammer and the anvil, you see the forging hammer is there, and there is you see the clear relation between the surface contacts which we are representing the springs at the concrete block and the hammer itself. And then even we can apply the similar kind of concept to the IC engine, which is mounted on the flexible base. So, IC engine is representing 1 degree, and you see we have a base over which you see the entire system is rotating, that is the another degrees of freedom system. We can say either the welding floor or anything. So this like this is a clear representation which you can see that we have this entire like the forging hammer, and this is my concrete block. I can represent this entire hammer as one mass, the discrete mass. Another discrete mass is basically from the concrete block. In between we have the like the deformation, that is nothing but the elastic deformation. The springs are there. We can say right now the spring stiffness is K1. The concrete block is at like a certain surface, and they have some kind of the deforming features that also can be represented by the springs, and that we have the K1. So right from the base we have first spring K1 stiffness, then we have mass M1, then we have like the K2 spring, and then mass 2. So this is here we have two independent displacement x1 which is related to M1 and x2 related to M2, which we are using here. We can say this system is absolutely falling into 2 degrees of freedom. And when we are trying to formulate the equations, we know that the basic equation in which the system is like at the equilibrium position under all the influences of the mass the forces, we can say this is nothing but equals to mx double dot plus kx plus cx dot equals to f of t, the forced exciting systems. And if we are considering, say, we have, since the damping is there and the property of damping is, say, under damped system zeta is less than 1, then we know that the complementary function, which is simply a representation of your free vibration condition, is nothing but equals to e to the power minus zeta omega n t. This is not one of the exponential decay due to the undamped natural frequency into a cos omega dt plus b sin omega dt. This is like one of the representation of complementary function, which says that you have a clear decay of the vibration amplitude with the exponential like decay, and the sinusoidal features are being there, means both the transient, the oscillatory term, and we have the sinusoidal features together. And to obtain the particular integral, which is nothing but the representation of your steady state formation, certainly it is subjected by the forced vibrations, the forced whatever the exciting frequencies are. So we can represent now by this phenomena with this equation mx double dot plus cx dot plus kx equals to f0 sin omega t. And if you just want to find out this one, certainly now we need to see that what exactly the nature of force is. And as you see, like we have f0 sin omega t, which is nothing but the simple harmonic force excitation with the f0 the initial force input, and omega is whatever the forcing frequencies are. And it will certainly like respond in the harmonical way at the same frequency which we want, at which the subject is excited. And there will be a phase lag in the output and the input part. Since input we are giving f0 sin omega t, so output which is coming in terms of displacement, there may be a phase lag. So you can see that if we have the input f equals to f0 sin omega t, then our output may be of x0 sin omega t plus minus whatever it's a phase lag. So like whatever plus minus phi is. We can represent by the graph you can see on the screen. This here the firm line which is simply showing our input force. The force is simply going at certain frequency, say omega. At the same frequency even we are getting the displacement output, but there is a phase lag, and the phase lag is this dotted line is showing the output which has maybe the less amplitude as compared to the force, but we have a clear phi. You can see it is simply showing by the red feature. There is a phase lag there in that. And this phase lag is mainly due to whatever the system characteristics are, that how the system is responding as you apply the force on the system. When we are now trying to simulate these things in terms of the steady state solution or a particular integral solution Pi1, we can see that the Pi for this kind of feature is nothing but x of Pi equals to x0, which we got sine of omega t minus phi. And if we are now going into the basic equation, that is mx double dot plus cx dot plus kx equals to f0 sin omega t, then we can get the output x0 is nothing but equals to the f0 by k, that is my input feature f0, and k is the system's property, divided by 1 minus m omega square by k whole square minus like we can say c omega by k. Or else even we can simply show with the various two different features. One, we can say that there is like a frequency ratio. the frequency ratio, sometimes you see here you can represent that what the exciting frequency, the forcing frequency is, and what is the exciting natural frequency. So, if we want to just convert this, sometimes in many of the books you will find that we have a frequency ratio R is nothing but equals to omega by omega n. Omega is your forcing frequency, omega n is your exciting natural frequency. And even we can represent this by the zeta, that is the damping ratio, C by Cc, or we can say that you see here, like when you have the omega n, which is nothing but equals to square root of by k, square root of k by m, you can put those things there itself. So, when you are simply calculating now what you have, when you are simply describing these things, x into k in the second equation, x into k by f0 is nothing but equals to 1 divided by square root of 1 minus omega by omega n whole square into whole square plus you see 2 zeta omega by omega n this one. So, again as I told you, omega by omega n you can replace this omega by omega n by the frequency ratio, and then you see here the zeta has already come out because of your damping is present in the system. So, now what you have this x by f0, this is nothing but equals to your frequency response, the outcome is there, or we can say it is FRF, frequency response function, because what you have output x0, you have input f0. This ratio is simply giving the relation that how your output is affecting when you have input f0, and it is being affected by two main feature, omega by omega, and that is a frequency ratio, and zeta, that is nothing but your damping ratio. And then the system's properties are there involving in the formation of R and zeta, your damping ratio and the frequency ratios. And then also we can calculate this tan theta, that is nothing but equals to how much you see the phase differences are being coming out in this. You can see that it is nothing but equals to 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. So, again you see here either in formation of the phase or in formation of the ratio of output by input, these two, the frequency ratio omega by omega n and the zeta, are playing a key role. And then you see here when we want to design certain things, we can simply control these two features as it is. And the total solution, if you want to get for this particular forcing frequency, including the complementary function and the particular integral for this underdamped system, we can simply see that we have x of t is nothing but equals to 1, the complementary function, which is simply showing your transient response, is nothing but equals to e to the power minus zeta omega n t into a sin omega dt plus b cos omega dt. That is the one part, and another is x sin omega t plus phi or minus phi, whatever you can simply put that. So, here the values of a and b, the constants, can simply calculate using the initial condition and the boundary conditions for the forcing functions are, that how the forcing function is carried out during the motion. A closer analysis of the above equation yields that you see for a very large value of t, means if we are going for say higher value of the time for which we just want to solve the equations, we know that the transient response which is coming out from the complementary function becomes very small, because your forcing factor at the time is playing a key role to carry out the solution. And hence the term steady state response, which is coming out due to the particular integral, is assigned to a particular solution, or we can say that the second term is dominating in the solution when we are just going for large value of t. And the value of coefficient for the steady state response, or we can say particular solution, becomes very large when you see the exciting frequency is very close to undamped natural frequency. Means you see here when we are very when the system is exciting close to your natural frequency, we know that the particular solution is really significant at the time. So, this phenomena where the system is going towards your natural frequency is known as the resonant frequency or the resonant concept, and it plays a real good role, because you see at that time we know that the huge amount of energy is being explored from the system, and we can say if we can control this part, if we know that you see this much huge exciting vibrations are there, or we can say the amplitude is there, this feature is really playing a vital role in the design or vibration analysis or in testing of any of the subject. Now this concept we would like to apply into the numerical problem and how we can play with some numerical data. So here we have the fourth example of this chapter, in which we just want to compute that what exactly this solution feature is, what is the generalized solution if the system is constrained by this boundary condition and this equation. So we have the equation x double dot t means the acceleration plus 0.4 velocity x dot t plus 4 displacement x of t equals to 1 by root 2 sine 3t. So we have a clear feature of acceleration, velocity, displacement, and 1 by square root of 2, that means you see the initial force, and sine this 3t, that is your natural frequency feature, the forcing feature from that. The initial conditions are also given to us, that x of t, x of 0, the t equals to 0, it means is minus 3 by root 2, and x dot 0, the initial velocity, since you see it is a linear term, so it is 0. Now first, like we would like to solve for particular solution or pi, you see here. So for that we can simply assign, we know that the forcing factor is coming from sine 3t. So certainly we have x of p, the particular solution in terms of displacement, is nothing but equals to x1 sine 3t plus x2 cos 3t. And then you see here we can simply find out the differential feature of this displacement, that means you see here what exactly the velocity and acceleration terms are. So when you are just deriving this, differentiating with the one derivative, the velocity is x dot t is nothing but equals to 3x1 cos 3t minus 3x2 sin 3t. Or else even we can say that if we are simply applying this one to acceleration term, then we have final x double dot p for a particular solution of t is equals to minus 9 x1 sin 3t minus 9 x2 x2 cos 3t. And now you see here, once you have these, now we have what? We have the displacement, we have the velocity, we have the acceleration. And if we are now applying these both, like all these terms towards your first main equation, which was x double dot t plus 0.4 x dot t plus 0.4 xt equals to this one, if you are applying this there, then you see we are ending up with this equation. This is nothing but equals to minus 9x1 minus 1.2 x2 plus 4x3 minus 1 by root 2 sin 3t, and the same you see here minus 9x1 minus 9x2 minus 1.2 x1 plus 4x3 cos 3t equals to 0. What we have done here, we have simply configured the entire equation into sine and cos feature. And we know that since the sine and cos features are independent, so certainly you see the coefficient of like the sine and coses are supposed to be equals to 0. So you see here we can frame these equations as minus 9x1 minus 1.2 x2 plus 4x3 minus 1 by root 2 equals to 0, and similarly you see the second form minus 9x2 minus 1.2 x1 plus 4x3 equals to 0. And you see we have what? The two equations, the two unknown coefficients x1 and x2, and we can get, you see, the solution of these equations by simply solving the coupled feature. So what we have, the final solution of a particular integral x of p is nothing but equals to minus 0.134 sin 3t minus 0.032 cos of 3t. So this is something you see which we have right now in our feature, that we are simply bounded the entire solution with this particular integral, which simply shows that okay, there is a displacement and the displacement is of this nature, in which you see the excitation is there from sin 3t and cos 3t. Now the natural frequency is nothing but equals to from the first equation x double dot plus you see here 0.4, we can say x. So 0.4 is our k, and since x double dot there is no, we can say multiplication in terms of mass, it is 1. So we have omega n is nothing but equals to 2 radian per second. And with this now we can calculate the zeta as well. The zeta is nothing but equals to 0.4 divided by 2 omega n, or else we can say it is 0.1. So certainly the system is now under damped system. And with this, you see here we can calculate the damped frequency because there is a damping which is available there. So damped frequency is nothing but equals to omega n square root of 1 minus zeta square, because zeta is here less than 1. So probably we can get 1.99 radian per second. So now you have both the exciting frequency, you have omega n, you have omega d, and you have zeta. So with this particular feature, now we can calculate the other features of the system equations. Now since this is underdamped system, so the complete solution is of the form of both the complementary function, which is nothing but equals to e to the power minus like zeta omega n t into like the a sin omega dt plus b cos omega dt, and particular integral which we just get the like outcome, that is x1 sin omega t plus x2 cos omega t. And when you are differentiating this equation with respect to the time, you have now x dot t is nothing but equals to e to the power minus zeta omega n t into omega dt a cos omega dt minus omega d b cos b sin omega dt, plus then you see you can further divide this equation into the differential form of your omega. So omega x1 cos omega t minus omega x2 sin omega t minus, now once you put entire thing, then the zeta, since it is the exponential term, so again you see this feature will come into the equation. So minus zeta omega n, which is nothing but the coefficient of your t in the exponential term, will come out, and it is minus nothing but you see minus zeta omega n into e to the power minus zeta omega n t into this the same like the omega dt coefficients in terms of sin and cos. Now if we apply the boundary conditions which we have already formed there in the initial feature, that you have x0 and you have x dot 0. When we are applying these equations to there, then we have this x0 which is nothing but equals to, you see, b plus x2 equals to this one, and we can get this b as nothing but equals to 2.089. Similarly, we can apply the same boundary condition x dot 0, which is nothing but equals to 0. When you are applying these things, then we have the value of a in the second equation. The a is nothing but equals to 1 by omega d zeta omega and b minus omega x1, and when we are applying this condition there, we have minus 0.008. So from these two boundary conditions, that is why you see the boundary conditions are very helpful in finding out the real feasible solution of any equations. Though you see the solution is bounded with particular integral or the complementary function, but the boundary conditions are always giving you some kind of direction that how the system is really behaving under this situation. So we can find the final solution, that is nothing but equals to x of t is equals to e to the power minus, since you see that it is minus term because there is a decay is there, so minus e to the power minus 0.2 t, like we know that this zeta and omega and both are simply giving the multiplication of 0.2. So we have this one, and then since it is already there the a and b, so a is minus 0.008. So we have 0.008 sin frequency was there, you see the like omega 1.99 t, so it is 1.99 t plus 2.089, that was you see the coefficient of b into cos of 1.99 t, and then you see the previous which we have already calculated for particular integral minus 0.134 sin 3t plus minus 0.032 cos 3t. So this is how you see we are dealing with this forcing factor and all other factors like omega n, you see the zeta and all other things, that how they are going to vary for a particular solution. So this numerical problem is simply giving one feature, that when we are like when you are just calculating some natural frequency or other phenomena, we have to be very careful that what exactly the boundary conditions are and how the system is propagating when the vibrations are being there under forcing factors. Now we are going towards the conceptual feature of 2 degree of freedom system, that how the 2 degree of freedom system is really behaving and how we can put the Newton's law towards you see formation of a equation of motion. So there are various steps which are being like involving to analyze the 2 degree of freedom system under the vibrating phenomena to get the natural frequency, because we know that since the system is moving at 2 different like we can say natural coordinates or independent coordinates, certainly we have more than one natural frequency, we have more than one mode shapes. So to resolve these, we need that you see whether it is under the forcing factor or what. So when it is like the restoring forces are being coming, then how the springs is being deflected. So you can see that we have a general system, the two springs are being simply constrained, the two masses, and both masses are at the displacement x1 and x2, and then we can see that since the springs are there, they have the stiffness properties, the spring rate, you see we can say K1 and K2, M1 and M2 are the masses, x1 and x2 are the displacement. With this now, first of all, we just want to resolve the forces when the springs and the masses are moving relatively. And when we are doing these things, you can see that when the forces are being exerted on that, on top of that, the red line is clearly showing that how the restoring forces are being diversify towards other side. So x1 and x2, since they are in this direction, the K1 is just going towards the main rigid frame, and x2 is going towards the free expansion feature. So this is, you see, like the elastic deformation of the spring according to their stiffnesses K1 and K2. And in that, you see here, if we really see that okay, the deflections are being there in the corresponding motion, so in other way they may be in the, you see the x1, this K1 is just going towards the free vibration, the free end, and x2 is going towards the rigid end. So these are the two possible combinations which can be there in terms of the restoring forces according to their stiffnesses. Or else if you just want to generally generalize this thing, then we have the on M1, on one side we have K1 x1 because the spring is well connected to this part, and it has, you see, the restoring property towards that. So restoring force for this is K1 x1. And on other side of the M1, we have the restoring forces which is basically due to the relative displacement of this spring from K1 and K2. So we have K2 into x2 minus x1, and for M2 you see here, since it is a free end, so other side there is nothing. And since they are in the balance condition, so in between the M1 and M2, the same force K2 into x2 minus x1 is applied in the action and reaction feature according to the Newton's law, since it is a well balanced criteria. When we apply these conditions to get this equation of motion, we can straightway go first to M1 mass, and for M1 mass we know that the force balance equation says that the inertia force due to the mass rotation M1 x1 double dot is nothing but equals to minus K1 x1 into minus K2 x1 minus x2. And with this, you see here we can frame the equation of motion as you can see on your screen, M1 x1 double dot plus K1 plus K2 x1 minus K2 x2 is equals to 0. Similarly, we can apply the similar concept to mass M2, where the force balance is just with M2 x2, that is the inertia force, and there is a restoring force which is coming out in between M1 and M2 because the spring is connected to both the sides. So we have K2 into x1 minus x2. So the equation is pretty simple, that M2 x2 double dot minus K2 x1 plus K2 x2 equals to 0. So we have a coupled equation of second order ordinary differential equation, and you can see that in this we have both. In the first equation we have a clear representation of x1 and x2, in second equation we have a representation of x1 and x2. So that means it is a coupled equation, and in that you see here we can simply form a state, we can say state space form, or rather you see, since we are only dealing with 2 degree of freedom, we can write independently this equation as you can see on your screen, M1 x1 double dot plus this and M2 x2 double dot plus this one. And we know that this equation is simply representing a simple harmonic motion where you see the input parameter and the output parameters are just showing the periodic solution. So we can say that x1 double dot is nothing but equals to minus omega square x1. This is a well known theory, you see, because we know that when you are just taking, say, the simple harmonic motion, so x1, if you are saying it is a simple harmonic motion, so x1 is nothing but equals to a sin omega t, then x dot 1 means the velocity is nothing but equals to omega will coming out, so omega a cos omega t, and x double dot, the double derivative, is nothing but equals to minus omega square a sin omega t. Since a sin omega t which we already consumed that it is x1, so we can replace this x double dot is nothing but equals to minus omega square x1. This is a well known feature of any sinusoidal excitation. So we can replace this now, acceleration x1 double dot is equals to minus omega square x1 and x2 double dot is minus omega square x2. And when we are keeping these things, so what we have now, we have the equation minus m omega square x1 plus K1 plus K2 you see into x1 minus K2 x2 in first equation, and when we are replacing this x2 double dot from minus omega square x2, so we have minus m2 omega square x2 minus K2 x1 plus K2 x2. We can frame the simple equation with this particular omega square in the matrix form, because you see the two equations are there and they are representing the same, like the independent coordinates x1 and x2. So we have now minus omega square m1 0 0 m1 and 0 m2. This is my mass matrix into x1 x2. These are my state space feature, plus now when we are taking this right from in the first equation, what we have K1 plus K2. So the first element in my stiffness matrix is K1 plus K2, then minus K2 from this side, and in the lower equation we have minus K2 and K2 in this x1 x2 is equals to 0. So in a broader manner now we can write the same equation in K minus, since it is we have the stiffness matrix, so K stiffness matrix minus omega square mass matrix into the independent coordinate x1 x2, that we are saying that the displacement, the relative displacement in between the masses m1 and m2, so we have x factor equals to 0. So this is, you see, the standard equation for showing more than one degree of freedom system when you see the system is excited with the various degrees of freedom. This equation can be shown to 2 degree, 3 degree, 4 degree, or any multi-degree system, multi-degree of freedom systems, where we have some of the properties, and this is something, sometimes we are saying that this is the cross check also. So the stiffness matrix K is K1 plus K2 in the first element, minus K2 as the second element, minus K2 on the lower side third element, and K2 as the fourth element. Mass matrix is M1 0 0 M2. Mode shape, which is nothing but equals to the relative displacement of the masses, they are simply x1 and x2. And when you see we are calculating the eigenvalue, that is the characteristic root of the equation, they are simply giving the natural frequency square root of this one. So first 2 degree of freedom system, there must be the 2 natural frequencies, because 2 equations are there and 2 masses are moving with the 2 stiffnesses. Certainly we have the 2 different exciting frequencies with these terms. And then you see, since the 2 natural frequencies are there, every natural frequency is corresponding to the mode shape. So we have 2 mode shapes in that case. And one of the important, or we can say the significant term in this, is the mass and stiffness matrices must be symmetric. If they are not in the symmetric way, you cannot get the equilibrium feature in any dynamic situation. So this is in reverse way, we are saying that this is the cross check for that. So the mass matrix is showing on your screen is M1 0 0 M2. So you see the diagonal, all the masses which are playing a critical role in formation of the equation or the exciting frequencies, they are always coming as in the diagonal form. The main diagonal element is always be positive, and for any large number n degrees of freedom system, the many numerical the techniques are there for that. We can resolve the issues according to time integration techniques, analytical formulation, or anything, even the discretized techniques as well, like in finite element, finite volume, anything like that. And in that you see what we are trying to see, if we want to calculate this, we are just saying that we just want to find the determinant of the matrix which must be equals to 0. So when we apply to this concept to any the matrix form, we have K minus omega square m into x equals to 0. If we want to find the solution, we need to go with the determinant. So determinant K, the matrix K minus omega square m equals to 0, or we can say the x equals to 0, the mode shapes, they are in the well balanced feature. And in this particular case, now we can say that for the non-trivial solution, we have the determinant K1 plus K2 minus omega square, that is one term, minus K2 was another term, minus K2 was the third term in the lower, and then K2 minus omega square m2 equals to 0. Or else you see, if we resolve this issue, we know that we have K1 plus K2 minus omega square and K2 minus omega square minus K2 square equals to 0. When we are trying to solve these equations, we know that the above equation is always in the quadratic form, the omega to the power 4 in the natural way. So 2 natural frequencies are there, one is omega n1 which corresponds the first mass, omega n2 which corresponds to the another mass of this with the stiffness value. So the first natural frequency and the second natural frequency, the nature of the natural frequency existing with any kind of system is like that the first natural frequency must be less than or equal to second natural frequency. It cannot be greater than that, because as it is like moving further, we know that the higher order excitations are creating more exciting frequencies. And when we are inserting this natural frequencies into the basic equation, say 1 or 2, then we can simply find that the determinant k minus omega n square m equals to 0, and determinant k minus omega n2 square m equals to 0, and correspondingly we know that we can get x1 and x2 because they have the linearly dependent parameters on these features. So x1 and x2, the relative displacement is giving some value on that. So now if we are using this, what we have first, minus m omega square x1 plus k1 plus k2 x1 minus k x2, that was our first equation, and if we are applying this, we have x1 by x2 at the first natural frequency is equals to k1 plus k2 minus m omega n1 square divided by k2. And similarly for the second mode, means at you see here omega equals to omega n2, we have this one. And since you see we are taking the relative displacement, right now we are saying that x2 by x1, that is nothing but the relative displacement of output by input, is equals to 1 for one part and another for minus 1. So 1 and minus 1 are just showing the phases in between the first and second, as in the diagram we have shown that the restoring forces are moving towards one direction, towards AND or free part, or in the other diagram also it was just you see like in case of repulsion. So in both the cases you see the displacement x2 and x1 are just 1 or minus 1. As you can see here in this also we have you see like the red feature, they are showing either in first phase they are just going in a similar phase part, both are in the extension feature, or in other part you see here it is simply you see one part is going forward, other part is just coming towards that side, so we have minus 1. So this is the first case is showing one feature, the masses which are moving, if they are in the phase they have plus 1 x2 by x1. The masses when they are just in the out of phase, means x1 is just moving positive and x2 is moving minus 1, we have always in the opposite phased feature. And mode shape are nothing but, as we already discussed, they are the relative displacement of the bodies at the different frequencies. We can show these things, that how you see, since we have the two masses, how we can say that they are in phase or they are out of phase. So you can see that in this first mode, when we are saying that they are absolutely in the opposite phase, you can see that both are just in like diagonal to each other. One is going down, one is going up, one is going up, one is going down in the first mode. While in the second mode, you can see that they are in phase, that means both are coming together downward direction or upward direction. As you see these are the two masses connected to the two springs, they have the same relative movement in the second mode or in first mode, irrespective of whatever it is. So accordingly you see we can say that x2 by x1 are 1 or minus 1 according to their relative motion. So 2 degrees of freedom system showing 2 natural frequency, 2 mode shapes, and both mode shapes are simply the relative displacement of their masses towards that. And 2 masses which are being constrained by the spring, certainly we have 2 different like the restoring forces on that, and we can show these things, that you see how the masses are being like encountered towards that. So please remember that whenever we are discussing about like the mode degrees of freedom, they are simply reflecting that the masses which are being connected by these springs or any of the constraint, they have relative displacement towards that. And say if you are going towards 3 degrees of freedom, certainly we have the masses sometimes in phase or out phase together. Maybe you see out of 3 masses, the 2 masses are in phase, 1 mass is out of phase, or even all 3 masses are in the phase. In that we are saying that this is the orthogonal condition. So sometimes you see when you are going towards the higher orders, generally we are saying multi degrees of freedom system, the orthogonality is one of the key property in the mode shapes. And we can calculate the mode shapes, means we can calculate the relative displacement of all the masses according to their exciting frequencies. And that is why you see here, if you are saying 3 degrees of freedom, we have 3 natural frequencies. If you have 4 degrees of freedom, 4 natural frequencies are there, or n degrees of freedom, simply giving you the n degrees of freedom systems. Now you see here we are applying the similar kind of concept to another feature, that if you see the end is not free, if the end is even constrained there. So you look at that, what we have m1 and m2. These are the two masses which have the displacement. The displacement is nothing but equals to x1 of t and x2 of t. These two masses have a clear constraints right from the beginning to the end. So we have in the beginning the K1 and C1, the stiffness and the damping. In between these two now we have K2 and C2, and in the last at the constraint feature another at the outside we have K3 and C3. So this system is now having the three, like the damping feature and three spring features, the stiffness feature. And now we are applying the force to introduce x1 and x2. So for m1, the force is which is being applied, the forcing factor is f1t and x1t is corresponding resultant. f2t is being applied to m2 and corresponding the displacement is x2t. We know that under the force excitation the system is well established, the equilibrium feature. So we can find out that you see the inertia forces which are being generated due to the force application on the masses m1 x1 double dot is nothing but equals to f1 which is being applied x1 by t. This is one part, means you see what you have displacement x1t, you have displacement x2t, and then you see you have the velocity component x1t and x2t because the damping is there. So velocity is also one of the important feature in dissipation of the energy as the viscosity is there. So please remember that if the system is simply a mass and a spring, the displacement is enough to find out the characteristic features of the system. But when you have the damping involved there, then we need to check that how the frequencies are being affected by this damping due to the dissipation of energy. That means in other way we need to consider the displacement and the velocity together. So we have, like right now the system is integrated with the spring and the damping here. So we can say that it is f1 x1t x2t x1 dot t x2 dot t and the t, because the time is because it's a dynamic feature, so we have the time. So this is for the first mass. We can apply the similar things to our another mass m2 x2 dot, which is nothing but equals to f2, or we can say like this particular function of x2t x1t and then x1 dot t and x2 dot t. So this is, you see, either the inertia force at first mass, inertia force at another mass. Certainly you see this is a function of both the displacement and the velocity component together. And now you see if we are applying the balanced condition there itself, then what we have f1t f1 which is like the forcing factor there on the first mass is nothing but equals to minus k1 x1t, because you see the restoring forces which is just coming out from the base. So minus x1 you see here is the displacement and k1 is multiplication, so restoring force, minus k2 x2 and you see when we are talking about the k2, this k2 is in between the displacement x1 and x2. So certainly we have the relative displacement. So this k2 is influenced by x1t minus x2t. And then you see here if you are going towards the viscous damping, again you will find that from the base end the c1 into x1 dot t, that means you see we have c1 velocity minus c2, because you see the c2 is also coming in between the two different displacement x1 and x2. So certainly you see there is a velocity difference which is coming out, and which or else you see which has like direct influence on the damping forces formulation for the first mass balanced feature. So you see we can say it is c2 into x1 dot minus x2 dot in that, and plus you see here whatever you see the forces which are being applied to the system f1t. So this is the total force which is being there, and we can simply formulate the equation of motion for this first mass. Similarly we can go to the another force, that is f2 on the another mass. So what we have, see straightway we can go to the k2. So k2, since it is coming in between x1 and x2 in the previous figure, so k2 into x1t minus x2t, that is a relative displacement feature. And then you see we can say that minus, now we have k3. The k3 is nothing but the spring stiffness which is just you see on the extreme side of mass m2. So since this is coming as the independent coordinate of your x2, so we have minus k3 x2. Similarly, we can say that when we are simply playing with the c2, which is in between you see your x1 and x2, so certainly the velocity differences are being there as x1 dot minus x2 dot. And then you see c3, which is like the extreme end, your damping feature. So c3 into x2 is your damping force at the extreme end plus whatever the force which is being applied to mass. So when we apply these equations, both f1 and f2 equations, the balanced equation, then what we have the equation of motion like that. So equation of motion is mx double dot, the inertia forces for first displacement. Second, we have the damping forces c1 x1 dot plus c2 x1 dot minus x2 dot. So this is the total damping forces which is being straightway applied to both the side of the mass just to make the balance or the energy dissipation. Plus you have the springs, since this mass m1 is connected by both side spring, one is k1 and one is k2. So k1 is affected by x1 and k2 is affected by x1 minus x2. And when we are doing these things, then it is equals to whatever the force which is being applied to the system external force. So this is the well balanced equation from the Newton's law, and we can say that we can apply the similar kind of situation to our another equation of motion m2 x2 dot is you see into c2 x1 dot minus x2 dot plus c3 x2 dot. So again you see here, this is the total damping on the mass m2. On left hand side we have a relative displacement x2 and x1 and x2. So you see the velocity component is coming in formation of damping force on left hand side in x3 x1 and x2, and on other side we have x3 dot, which is nothing but you see, since it is an independent coordinate with the c3, so we can calculate this x2 dot into c3. And similarly you see for restoring forces, on the left hand side of m2 we have a relative displacement between x1 and x2. On other side, on right hand side of mass m2 we have an independent coordinate of x2, so we can calculate you see the k2 and the k3 formation accordingly, the restoring forces. And then you see the f2 which is being applied force on the mass m2. So these two equation of motion is simply shows that how you see the damping, restoring forces, and you see the inertia forces are being well balanced even when it is being applied by external force F1 or F2 on M1 and M2 masses. Then you see again we need to, if we want to solve this, then again we need to apply the same, that you see since these forces which are being applied to the system, they are harmonical forces. So we can simply assume that even F1 is nothing but equals to F0 sin omega t, F2 which is nothing but equals to F0 sin omega t in other way, and then you see you have the two forcing factors. The entire system is under periodically exciting figure, or we can say simple harmonic motion. You can apply you see same that x1, since you see you have the 2 degrees of freedom system with the x1 and x2 displacement, you can say x1 double dot is nothing but equals to minus omega square x1, x2 double dot is nothing but equals to minus omega square x2. And when we are applying these conditions, we can frame the same equation as the matrix K. In this particular feature matrix, now we have the more number of elements, because what we have, since you see it is a 2 degree of freedom system, but there is a clear interaction of 3 springs. So we have you see in our elements we have K1, K2, K3 interacting together. And in the same you see we have the damping figures. So now there is a damping feature which will come out, because now the system is also exciting with this particular phenomena. So we have what? We have undamped natural frequency and the damped natural frequency. We can simply calculate that whether the system is underdamped, critically damped or overdamped, and accordingly you see we can frame the equations there itself for the solution. And then we can find out that what is my outcome is there. So x0, or you see here x2 by x1 according to the mode shapes. So in simple way, that simply like it is a 2 degree of freedom system, we can resolve all the issues by assuming the simple harmonic motion input excitation and output feature x0 in the simple harmonic motion. So the frequency response functions can be calculated, mode steps can be calculated, or the natural frequency can be simply like obtained using these equations omega n1 and omega n2. So matrix and vector notations can be incorporated into these equations, which is useful for like generalizing an arbitrary number of degrees of freedom. So we can use the similar kind of steps to solve even the n degrees of freedom system. So in today's lecture, most of our discussion was like that if the system is under forcing factor or the system is of 2 degrees of freedom, then how we can resolve the 2 degrees means the 2 coupled equation, how we can give the input features of the simple harmonic motion, or how the boundary conditions or the initial conditions are being straightway applied to get the final numerical solution. In our next lecture, now we are going to discuss, because you see till now you see we were discussing about this 2 degrees of freedom. So, we would like to now finish up to, we will go up to certain higher degrees, and we just want to see that how the forcing factor, the free and forced vibrations are there for more than 2 degrees of freedom. Generally we are saying that the multi degrees of freedom, because as we know that the theme of this course is basically the vibration control. So, control strategies should be applied at the main exciting frequency. So, from these you see we could figure out easily that how like the exciting features are being taken place at the system, which part is exciting at like more, or what exactly you see like their phases when all the masses are being applied like under the exciting frequencies. Okay, thank you.